All right. Here we are for 4.3. And what I actually want to go back to, something I didn't go back to for 4.2. We looked at this at first to see how amplitude changes things. So here's our generic sine function. And we've talked about what the capital A does, changes the amplitude. So with nothing written there, a is a 1, but as we change a, then this function grows, and when a goes negative, it's flipped upside down. So remember, the sine function starts in the middle and goes up, but if we multiply by a negative number in front, it starts in the middle and goes down instead. All right, so the capital A changes the amplitude. Capital B, B times the variable, changes the period. All right, so with nothing in there, it's an unwritten 1, but as we change b, we change the length of the cycle, which ends up stretching or squishing the graph horizontally instead. So, for example, as b gets bigger, remember the formula is for the new period is 2 pi divided by b. B is in the denominator. So, if b gets bigger, it actually makes the period get smaller. So here's our usual sine function. Starts at 0, ends at 2 pi, right? That's the length of one full cycle. Well, when b gets bigger, like if b is 2, for example, now the period is half as long. It goes through its whole cycle, and it's finished by the time it gets to pi. And as b gets bigger and bigger, the length of one cycle gets smaller and smaller, like so. Now the other possibility there is when b gets smaller, so when it's 1, well, when the denominator gets smaller, the fraction gets bigger, so 2 pi divided by b would get bigger, and sure enough, it stretches the period out instead. All right, so these first two letters that we've looked at, capital A is vertical stretching or shrinking, capital B is horizontal stretching and shrinking. Now, what we're going to get into in this section are the letters K and H, lowercase k and lowercase h. And these guys don't do stretching or shrinking like capital A and capital B. They shift things around. So letter K is the first one we're going to look at. And in where's our notes? We'll fill in some things and we'll look at this example. So if you see what we have here, we're taking this k and adding it to the function. So what we've basically dealt with before is the situation where k is 0. There is no other term there. We just have the sine function. But when you add a k into that in front of, it could come after as well, but we typically write it before. If we add that to the sine function or the cosine function, it causes what we call a vertical translation in the graph, which is translation is the mathematical word for sliding around, basically. All right, it doesn't stretch, doesn't shrink, it just moves it. And in particular, it moves it vertically. So in all of our previous examples, the x-axis was the center line of the graph. The graph went up the same distance to the peaks and the same distance down to the valleys. From that center line, from the x-axis. But now when we change k, it takes this whole graph and slides it up and down. So the shape is not changing, it's just moving up and down, that's all. All right, so it's actually not changing the amplitude, right? The wave itself is not bigger or smaller, it's just positioned differently. So whereas in the past, the center line of our graph was the x-axis right here, well, now when we change k, it moves that center line up and down to a different spot. We're going to have to mark it on our graph. So this letter k is going to have an impact on our vertical axis, not on the horizontal one, just the vertical. All right. So the center line, which was formerly the x-axis, or in other words, the line y equals 0, is now at y equals k. All right, so look at this example and how that changes things. So initially, 5 times cosine of k, that's what we've dealt with before. The amplitude is 5, all right, that number multiplying cosine. There's nothing multiplying the x, so the period is still 2 pi. But now the difference is we have this -2 in front. So the new center line, as I note here, is at y equals -2. So on the graph, we mark off -2 right here, and I usually put a dashed line across to mark our new center line. And then the peaks and the valleys occur at the appropriate places, starting at the middle and going up and down from it, whatever the size of the amplitude is. So our amplitude is 5, so starting at -2, we go up 5, and that would be 3, and we go down 5, and that would be -7. So that's where our peaks and our valleys are occurring now. All right, so while it used to be the x-axis and then positive and negative amplitude on the y-axis, now everything's shifted down 2 units in this case. So here's our center at -2, here's our peaks at 3, valleys at -7. Now our period was still 2 pi. We get these standard x coordinates on the x-axis there, and we're still starting at 0, but now when we are plotting points at the top, middle, and bottom of the graph, the top is right here, and this is a positive cosine function. Notice the 5 is positive. It's a +5. This is negative, but that does not have anything to do with what's multiplying the cosine. So it's starting at the top, goes middle, bottom, middle, top, like the usual cosine shape, and then we fill it in like so. Okay. Now, that's not too bad to adjust. It's just a matter of making some things go up and down, changing where things are noted on the y-axis. The other letter that's involved, the letter H, is actually, if you think about x as inputs, it's the first thing that's happening to x as an input. So we have x and we're subtracting the letter H. All right, and there's a good reason for why we're subtracting it. All right, so now all the situations we've looked at, basically H has been a 0 and then it's not written. But what H does now as you change it is take the graph and shift it to the left and the right. So again, no shape change, just a position change. And there you go, shifty shifty. So what that means for us, so in the past, our basic cycle that we graphed started right at 0. Well, now our basic cycle is not going to start at 0, it's going to start at whatever that H value is. All right, so you can see here it was at 0, and when H is 1.19, well, now our graph is starting at, and that's 1.19 right there. So the impact this H has is on our horizontal coordinates, and can make kind of a bigger mess out of those x coordinates that we mark off for our 5 key points. All right, so filling in the blanks, H, this new constant H, causes what's called a horizontal translation. So our basic cycle starts not at x equals 0 anymore, but at x equals h. And I think I'm going to go through a couple examples here, and we'll do those, and then there's group exercises for you guys to try as well. Okay, so I'm going to go to the document camera now. There it is. Just had to get things to focus correctly. So this is example 2, which is y equals 3 sine x minus pi over 5. All right, we're going to graph this guy. So, it's worth pointing out, there's nothing being added or subtracted in front of this, so there's no vertical shifting with this particular example. There's only going to be horizontal shifting. Now, amplitude, we got number in front of the trig function there, multiplying it, so amplitude 3. And with nothing, and maybe it's worth noting, our center line, now that we've started talking about this, is not shifted. Center line of y equals 0 is what we always dealt with before. So vertically, we're just going to have 3 and minus 3 to deal with. What's different here is that our starting and our ending point are going to occur at different places. So instead of x equals 0, this is going to start at this number. All right. Now, when this is subtraction, written as subtraction in our general form, and the reason that's written as subtraction is because then whatever this number is exactly what our starting spot is. All right. If you want to think of it as this start is the opposite sign of what's in there, that's fine too. But in general, this is going to be written as minus some h. So basically, if this is a plus, that means we're starting at a negative number instead. All right, so starting x equals plus 5, or x equals pi over 5. Period, I didn't mention. There's nothing multiplying the x. That's the number that changes our period, but there's nothing multiplying it. So our period is still the usual 2 pi. But then to see what difference that makes, we're not starting at 0 anymore, but that also means we're not ending at 2 pi anymore because the whole graph got shifted over. So the end is going to be at, well, pi over 5 is where we start. The end comes from adding 2 pi to the start. So we got to be careful with fractions and stuff here. So pi over 5, well, 2 pi, if you think of that as 2 pi over 1, we got to multiply the top and bottom by 5. So we get 10 pi over 5. So in other words, this thing's going to end at 11 pi over 5. So I'm going to mark off pi over 5 for the start and 11 pi over 5 for the end. We still need to figure out these guys in the middle. All right, and this is even more importantly where using the midway point between two numbers, using that little formula becomes especially important, because now a lot of the times when we do these, we don't have a 0 on one end, which simplified things. So for example, this guy right in the middle, he is halfway between pi over 5 and 11 pi over 5. Now, I keep saying this too, all these fractions are going to have pi's involved. So really it's just a matter of figuring out the numbers, the fractions. So this is 1/5 along with a pi. This is 11/5 along with a pi. So we're kind of asking what's in between 1/5 and 11/5. All right? And in fact, with the same denominator, it's even a matter of just thinking about what's halfway in between 1 and 11. And if you can answer that question, well, you'll expect the answer that's coming out here. All right, they got the common denominator, so we can add them up. 1 pi plus 11 pi is 12 pi's. Common denominator, 5. Cancel the 2 with the 12, and we get 6 pi over 5. There it is. So yeah, what's halfway in between 1 and 11? 6 is. Now, this guy and this guy, halfway in between these two. All right, 1/2. So between pi over 5 and 6 pi over 5. Add those up and we get 7 pi over 5. 1 pi plus 6 pi. And actually nothing cancels here, so we get 7 pi over 10. And that doesn't simplify. And then finally for that spot, halfway in between 6 pi over 5 and 11 pi over 5 is a total of 17 pi on top, 6 plus 11, 5 on the bottom, times the 1/2, 2 doesn't cancel, and we get 17 pi over 10. What lovely x values we got there. There they are. All right, so there's our 5 key points. Now, sine function, positive number in front. So start in the middle and go up. Now our start is not here, it's here. That's the big change. So start in the middle, go up. So hit the top, come, da, 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 da. We've done this shape before. So top, middle, bottom, middle, and put your sine wave in there, like so. Okay. Now there's one last thing I just want to illustrate on this example in terms of all these numbers, because it may just feel kind of like we follow these formulas and it just sort of feels random, but there's a definite pattern here. But you only see the pattern if all these fractions have the same denominator. So 2 of them have a 10, and if I change these 3 to have a denominator of 10, which means multiplying top and bottom by 2, look at what we got. So this would be 2 pi over 10, and we got 7 pi over 10. This would be 12 pi over 10, like so. We got 17 pi over 10, and this one, top and bottom by 2, would be 22 pi over 10. And now when you look at them, look at how nicely equally spaced these all are. They all have the same denominator of 10, and the same pi in the numerator, and the other numbers, 2 to 7 to 12, so up 5, up 5, up 5, up 5. Very nicely equally spaced. And sometimes that shows up and it's easy to see in these problems, and sometimes it's not so easy with different denominators and things like that. Okay. There's one more lecture example, and then a little summary, and then the group exercises, which I think I might do on a separate video again. All right. So next one is, so example 3, y equals 6 minus 4 sine. Now there's one little issue that pops up with this guy. So our basic formula has inside, so it was, so y equals k plus a sine, didn't leave myself much room, b x minus h, like so. So the inside the sine function, we have b and then x minus h actually inside parentheses. And if you look at what we have here, that's not exactly the same. All right, so in order to really nail down where things start and whatnot, we need to make sure this part in the square brackets looks like this. So it's some number times x minus whatever in parentheses. So this one needs a slight adjustment to begin. So it's going to be, we got 2 times x, so it's going to be 2x minus, and now something here. But if these two are going to be equal, what we need in this slot is what you get when you factor a 2 out of pi thirds, which may sound super intimidating, but I think sometimes the best way to think about this is in reverse. 2 times what is going to get you pi over 3. All right, so 2 times what fraction gives you pi over 3. So in other words, if we went back and wanted to get rid of these parentheses, we would have to distribute over the parentheses. All right, and so 2 times what gives you that? Well, the 2 would have to get canceled to leave pi over 3. So there's got to be a pi on top, and basically you need another factor of 2 down here to cancel that 2. So instead of 3, we just need 6. So factoring out a 2 is actually the same as just multiplying this by a half. We went from pi over 3 to pi over 6. Or, once you got an answer, check it. If I do 2 times that thing, do I get that? Do I get back where I started? That's the question. All right, now this is in the form that we've been talking about. And we're going to graph this guy. So, here comes everything. Amplitude. Well, we have a -4 in front of the sine function. And again, amplitudes are positive, so it's 4. Period. Well, we have a 2 in that slot. So 2 pi over 2, which means the period is just pi. That's not too bad. Center line, while it was normally y equals 0, we have a 6, a positive 6 in front of this thing. So so vertically, the center line is going to be y equals 6. And here's our h. All right, remember the basic form is x minus h. So here we have x minus pi over 6. So we're going to start at pi over 6. We will end at the beginning plus the length of the period, plus the length of one whole cycle, which we nailed down to be pi. So this pi is here because of this pi. All right, so 1/6 of a pi plus a whole pi is 7 total sixths of a pi. Or you can write this as 6 pi over 6, and if you add one more, you get 7 pi over 6. Okay, so here we go. Vertically, let's start with that. Center line is at y equals 6. And I'm going to put that in as a dashed line. There's our center. So where the peaks and valleys occur, take your center line and go up and down by the amplitude. So 6 up, so plus 4 gets us to 10, minus 4 gets us to 2. All right, horizontally, we start, I'm going to mark these down here, even though this is actually the middle of the graph. Start at pi over 6, we're ending at 7 pi over 6. Okay. So, what do we have in between? All right, kind of like the previous one. They're all going to have pi's. These two both have the same common denominator, which is 6, which is nice. So we're kind of just asking what's halfway in between 1 and 7. So 1/2 of pi over 6 plus 7 pi over 6 is 1/2 times 8 pi over 6. Which actually leaves us with a lot of stuff that can cancel. We can cancel the 2 and make the 8 a 4. We can cancel the 4, part of the 4, with the 6 in the bottom. And what we actually get is 2 pi over 3 in its most simplified form. All right, this guy, that guy right there, 1/2 pi over 6 plus 2 pi over 3. Well, we're going to need 6's on the bottom. So if I want to turn that 3 into a 6, I got to double it. So I got to double the top too. And we end up with 1/2, total of 5 pi's on top, 1 plus 4. 6 on the bottom, and actually nothing cancels this time. 2 times 6, though, makes 12, so 5 pi over 12. Lovely collection of different denominators here. And the last one, 1/2. Now again, 2 pi over 3 is 4 pi over 6 for that same denominator. 7 pi over 6. So we get a total of 11 pi's. And we'll have a 6 on bottom times 2, so 12 again. So 11 pi over 12. All right. So then we just need to plot our 5 key points. Now, sine function, but negative in front. So sine function starts in the middle. So on our center line, but at the beginning x-coordinate right here, negative sign goes down. So we would go at the next key point, we would be at the bottom. All right, there's our level for our valleys. And we turn around, so middle, hit the top at 10, and then back to the middle. There's our sine function. All right, I'm just going to point out again, too, these are simplified, which led us to have 3 different denominators. But if they all have the same denominator, which would have to be 12, there's a very nice pattern, and I'm just going to show that to you real quick. All right, so 5 pi over 12 is going to stay as it is, and so is 11 pi over 12. So pi over 6, if we want 12 on the bottom, that would have to be times 2 top and bottom. You have to multiply this guy by 4 top and bottom to turn that 3 into a 12, which means we got 8 up here now. And times 2, 14 pi over 12. And if you look at that list of numbers now, pi, 12, 12, 12, 12, 12, 2, and then we go up 3 to get 5, and then up 3 to get 8, and up 3, and up 3 for the 11 and the 14, and they're so nicely equally spaced, even though they're kind of bleh in terms of being fractions of pi and all that sort of stuff. Okay, so just to summarize, And this is back on the filled in notes. There's the one we just did. Here's the summary. So this is all the changes we have. So like we saw before, amplitude, absolute value of whatever A is. Period, 2 pi divided by B. Center line at y equals k. Our one cycle that we're graphing starts at x equals h and ends at x equals h plus the period. So this is 2 pi over b because this is 2 pi over b. So this, whatever this turns out to be, gets copied right into that slot. And you may have to simplify things. Now the last little thing I bring up, only because some of the homework asks you for these things, this number, if you multiply all this stuff out, so like if you go up to here and you actually get rid of the parentheses, you'll get b times x, and you'll get minus b times h. This thing, minus bh, is what's meant by the phase of a trig function. All right, so anyway, you just need to compute some of those and put them into some homework problems. I guess the other thing worth mentioning about the homework too is that all these sorts of examples that we're doing by hand can't do on WebAssign very well. But when it comes to taking the exam, you will be expected to be able to do some of these, put these together by hand, not just pick the right one out from a multiple choice question, which is what some of those WebAssign problems are like. So there's 2 pages of group problems here for 4.3. Go try them, and I will eventually get a video up going over them, and you already have the filled in version, final versions for those available to you as well. So go try them, see how they go, check them with the filled in answers, and I think that's it.